She's good at it.
Alright, who's heard of factorial notation before?
Pardon?
That's
Oh,
exclamation.
That doesn't answer your question.
Math is so exciting, they needed an exclamation mark in it. That's why. Okay, so we're going to be looking at factorial notation. Let's just explore what it means using an example. So consider how many ways there are of arranging 6 different books side by side on a shelf. So using the fundamental counting principle, we would first have 6 books to choose from. Once we put one book in place, we then only have 5 choices, 4, 3, 2, then 1. So rather than writing this out in a big long multiplication sentence, we're going to use factorial instead. So 6 times 5 times 4 times 3 times 2 times 1, we can just write as 6 factorial. So without using a calculator, let's figure out the value of 4 factorial, which is actually like 4 times 3 times 2 times 1. 24. Okay, then we're going to go 3 factorial times 2 factorial. So 3 factorial is 3 times 2 times 1. We're going to multiply that by 2 times 1. So we have 6 times 2 is 12. My marker's not working very well. Now there's a few different ways we can write factorial. We could write 6 factorial as 6 times 5 times 4 times 3 times 1, or we could write 6 factorial as 6 times 5 times 4 times 3 times 2 factorial. Because what's 2 factorial? 2 times 1. Or we could write 6 factorial as 6 times 5 times 4 times 3 factorial. Because what's 3 factorial? 3 times 2 times 1. And so on, so on. Okay? So, keeping that in mind, we are able to simplify factorial. So the table above can be used to help us simplify 6 factorial divided by 4 factorial. So 6 factorial is 6 times 4, or 5 times 4 factorial. And 4 factorial we can just write as 4 factorial. The 4 factorials will cancel out, and we're just left with 6 times 5 equals 30. So we're going to express 5 factorial as a product in 4 different ways. Okay, how about 5 times 4 times 3 times 2 factorial? Or 5 times 4 times 3 factorial? Or 5 times 4 factorial? Or just 5 factorial? I guess the only other way that would be the obvious one would be 5 times 4 times 3 times 2 times 1. Okay, we're just expanding the whole thing. So let's complete the following. 12 factorial can be rewritten as what times 11 factorial? 12, good job. Okay, 8 factorial can be rewritten as 8 times 7 times 6 factorial. 6 times 5 times 4 can be rewritten as what divided by what? What canceled out?
3 factorial.
Okay, the 3 factorials canceled out, right? So we could write it as 6 factorial over 3 factorial. And the 3 factorials would cancel out. So you might just want to show this expansion for this question here. Okay, what canceled out? 11 on, right? So we could write this as 15 factorial divided by 11 factorial. Because all the 11s, 11 times 10 times 9, so on, so on, so on, canceled out. Without using a calculator, simplify 10 factorial divided by 7 factorial. What are we going to be left with? Good. 10 times 9 times 8 times 7 factorial divided by 7 factorial. What's going to cancel out? 7 factorials. So then we get 72 times 10 is 720. Okay, next one. 8 factorial divided by 5 factorial times 3 factorial. We have 8 times 7 times 6. Do we want to cancel out the 5s or the 3s? What's going to be easier to calculate? Let's cancel out the 5s. So we're going to multiply by 5 factorial divided by 5 factorial times 3 factorial. Okay, so 5 factorials cancel out. And then we have 8 times 7 times 6. 3 factorial is actually like 3 times 2 times 1. What's the value of the denominator? 6. So we can cancel out the 6. And we're left with 56. 8 times 7. Isn't this stuff fun? You have to say it really excited though. So now instead of specific values in place, we're going to apply factorial with n, or variables. Okay, so in general, n factorial is equal to n times a number less than n times another number less than n minus 1 times another number that's less than that, and it's just going to keep getting smaller and smaller and smaller until you get to a multiplication of 1. So for example, remember we had like 8 factorial, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This is like your n. N minus 1 is 7. 8 minus 2 is 6. 8 minus 3 is 5, and so on, so on, so on, until eventually you get to the 1. Okay? Okay, and just keep in mind that n has to be natural numbers. Natural numbers are 1, 2, 3, 4, 5, 6. They don't include 0. They don't include negative numbers. Okay? N factorial has to be a natural number. I guess I just said that. 0 factorial, it's equal to 1, and we'll go through a proof of that later. And basically, n factorial can be written as a product, as we just saw. For example, we looked at 8 factorial. This marker's no longer working. Okay, 8 factorial, that can equal 8 times 7 times 6 factorial, right? Or it can equal 8 times 7 factorial. So that's just exactly what this is saying here. So if this was 8 factorial, we have 8 times 7 factorial. Or 8 times 7 times 6 factorial. It's just using variables instead. Okay, so if we had n factorial expanded, we would have n times n minus 1 factorial. 8 factorial is equal to 8 times 7 factorial. That's basically what it's saying. It doesn't have to be 8, it could be any number. N plus 2, it's going to start with n plus 2, and then we're going down by 1 each time, so then it will be n plus 1, and then n. I guess that's our last one, I can use the full space. N plus 2, and then n plus 1, and then 1 less than that will just be n factorial. Yeah?
Like, I don't really get how it goes from n minus 3 to 3 to 1.
So eventually, you're going to get to the digits 3, 2, 1. For example, if I continued this one, n minus 4 is 4, so 8 minus 4 is 4. 8 minus 5 gave me 3. 8 minus 6 gives me 2. 8 minus 7 gives me 1. So they just haven't shown these in terms of the number you're starting with, subtract, but eventually you will always get to 1 at the end. Okay? So it's just whatever number you've started at, it works its way down, multiplying each digit until you get to 1. Okay? Alright, next one we have n minus 4 times n minus 5 times n minus 6 all the way to 3, 2, 1. What does that equal? Right from the definition, n factorial. So now let's try and simplify these. Well, n plus 2 factorial, that can be written as n plus 2 times n plus 1. You see how it's going down by 1 each time? And then notice in the denominator I have n factorial. If I want to simplify it, I need to cancel that out. So I'm just going to keep going until I get to n. n plus 1 minus 1 is n. So I'm going to stop there and I'll put a factorial. N factorials cancel out, and we're just left with n plus 2 times n plus 1. And that's in product form, so let's just leave that, because it asked us to. Alright. Is n minus 2 bigger or smaller than n minus 1? It's smaller. So maybe we want to expand the denominator. N minus 2 factorial divided by n minus 1 times n minus 2 factorial. The n minus 2 factorials will cancel out, and we're left with 1 over n minus 1. So you have to think about which one would it make sense to break down. Because we want to end up so that, or we want to cancel out one of the factors basically. Alright, next one, n factorial divided by n times n minus 1. So we start with n, and then the next one will be n minus 1 factorial divided by n times n minus 1. The n's can cancel out. Can the n minus 1's cancel out? No, what do I have to do? I have to go one further to n minus 2 factorial. Then these will cancel out. So I'm just left with n minus 2 factorial. So knowing that we can simplify these factors in factorial notation, we can then solve equations. So we have n factorial over n minus 2 factorial equals 42. Let's just break down the n so that we eventually get to n minus 2 factorial. So n factorial over n minus 2 factorial equals 42. N factorial can be broken up or simplified into n times n minus 1 times n minus 2 factorial, all divided by n minus 2 factorial. So n minus 2 factorials cancel out, and now we have two factors that equal 42. N times n minus 1 equals 42. So we get n squared minus n minus 42 equals 0. Okay, if I move everything to the left-hand side and expand, and then it's just a quadratic equation that we need to factor and solve. So what two numbers multiply to negative 42 and add to negative 1, negative 7, and positive 6? So n will equal negative 6 and positive 7. Go back to the definition of factorial notation. What does n have to be? Natural number. What's my extraneous solution? Okay, negative 6, because it's not a natural number. Okay, so just keep that in mind if you ever end up with a negative solution. So now we're going to learn how to use the factorial button on our calculator. So for example, what if you had like 23 times 22 times 21 times 20 times 19 times 18 times 17? Do you really want to have to multiply all those numbers? Probably not. So factorial button. I just have to start this over here. Okay, we're going to go 6 and then math over to probability, and number 4 is your factorial button. And then press enter. Okay, so we get 720. Okay, let's practice one more time. 9 factorial, so we can go 9, you put the number first, so 9 and then math over to probability, number 4 for factorial. We get 362,880. Sorry, I should have erased this first. So you have to go over to probability at the top. Do you want me to show you one more time? You're gonna? Okay, so 720 and 362,880. So to simplify a quantity like 10 factorial over 7 factorial, 3 factorial on a calculator, we can evaluate numerator and denominator separately, then divide, or we can just enter it all at once. So for example, 10 factorial, 3 million such, and then 3 factorial times 7 factorial is 30,000 such. Okay, or we could simplify it. Okay, 10 times 9 times 8 times 7 factorial divided by 7 factorial over 3 factorial. 7 cancels out. Okay, and then we just multiply it through. So 720 divided by 6, and we get 120. So you could do it algebraically like that if you wanted as well. If you were to use your calculator, another way is just simply putting 10 factorial and then divide by, in brackets, 7 factorial times 3 factorial, okay? So you don't necessarily have to do this work. And sorry, I just showed that work from part 2, so we've done it. Okay, using our calculator, let's try to calculate 43 factorial divided by 40. You guys get 74,046? Okay. Okay, now the next one, probably easiest way is just go 37 factorial. And then divide in brackets the denominator. 33 factorial times 4 factorial. Just note that I didn't write 37 in that numerator, which is why I got such a wrong answer. So I'm just going to insert that 7. There we go. That looks better. Okay. 66,045. Anyone need a little help with their calculator? Good?
He's here to wonder. The highest you can go is 60. 70's overflow.
Okay.
70's overflow?
Yeah, 69's the highest you can go.
For what?
For this.
Alright, I need a reader. I keep stuttering my words.
An internet site access code consists of 3 digits. Knowing the 3 digits is not enough to access the site. The digits have to be entered in the correct order. The order of the arrangement of the digits is important. John cannot remember the access code except that it contains the digits 3, 5, and 7. List all the arrangements of these 3 digits that John could use to determine the access code.
Alright, so Bernie's got some highly classified information on his phone. We're trying to crack the code, kind of remember it's 357 combination somehow, if there is a 3-digit password on his phone. So let's figure out those possibilities. Alright, so we could have 357. We could have 375. Okay, we've used up 3 as our first digit now. Okay, we could have 537 or 573. Then we could start with 7, and it could be 735 or 753. So how many arrangements? 6 arrangements. Okay, or we could use the fundamental counting principle. How many options would I have? 3, 5, or 7? That means I have 3 choices. Once I've used one of them, then I only have 2. Once I've used one of them, I only have 1 more. So 3 times 2 times 1 is also 6. So we could have used the fundamental counting principle too. Okay, there are 6 possible arrangements to consider, and only one of them will access the site. This type of arrangement, where order is important, is called a permutation. Okay, a permutation is an arrangement of a set of elements in which the order of the elements is important. Okay, can't stress that enough. Permutation order matters. So permutations of n different elements taken n at a time. So let's look at the word cat. We could have CAT, CTA, TAC, TCA, ACT, or ATC. How many possibilities? 6, which is also like 3 times 2 times 1. Okay, so we had 3 options, then 2, then 1. So how could this be written in factorial notation? What's that? 3 factorial. Perfect. Okay, which the conclusion of this is we have 6 arrangements. Of those letters. So a general rule, the number of permutations of n different elements taken all at a time is n factorial. So if we have 3 letters and they're taken all at one time, the number of arrangements will be 3 factorial. Let's take a look at the word Regina. Okay? The number of permutations of the letter of each word, of the letters of each word. So Regina has how many letters? If we have to take them all at one time, which means we need a 6-letter word, but it can be in any order, but you can't repeat the letters. Okay, let's just go back to the fundamental counting principle. Start with 6, then 5, then 4, then 3, then 2, then 1. Well, a shortcut to that is there's 6 letters, 6 factorial. Okay, what is the value of 6 factorial? Practice using your factorial button. What do we get? 720?
2, 3, 4, 5, 6, 7.
Okay, so there's 720 permutations. Kelowna, how many letters do we have? 7? So 7 factorial equals 50,040? Perfect. So there's 5,040 arrangements. Good stuff. So basically we see that factorial notation, fundamental counting principle, it's the bare bones of permutations. So permutations of n different elements taken r at a time. So what we just looked at was the situation where we're taking all at a time. So it's just simply n factorial. But there might be a case where you're only taking 3 of the letters at a time, or 4 of the letters, not all 7 letters. So we have to consider a different case. Use the fundamental counting principle to determine how many 3-letter arrangements can be made from the letters of the word graphite. We have 1, 2, 3, 4, 5, 6, 7, 8 letters total. We need to create a 3-letter word. So for the first letter, I have 8 options. Then I have 7, then I have 6. So if we multiply that through, we get 336 possible arrangements. In this example above, we found the number of permutations of 8, which is n elements, taken 3, which is r, at a time. This is denoted 8 permutations. So we're basically like, we have 8 elements and we're taking 3 at a time. P stands for permutation, okay? 8p3 is like 8 times 7 times 6. And that's basically like 8 factorial divided by 5 factorial. Okay, and this 8 times 7 times 6 is what we did up here. That's how they got that. Okay, so there's 8 possible options. We need to only use 3 of them. So if we were to expand that, that's like 8 times 7 times 6 times 5 factorial. The 5 factorial is cancelled out before. Okay, but just expanding a little bit further, we could write this out fully as 8 factorial, and we get 5 factorial from 8 minus 3 factorial. This is generated the formula for permutations. Okay, the number of permutations of n elements taken r at a time is given as n factorial divided by n minus r factorial. Okay, so it's just a little shortcut when you're given maybe really, really big numbers or a lot of different elements you have to take at a time. You can just plug it in this rather than going through the whole thing. Okay, let's use the NPR key on our, or the permutations key on our calculator to evaluate 8p3. So I'll just show you where you find that. First you're going to have to
Junior
put
clock
8.
change.
Then you go to math, over to probability, and number 2 is your permutations key.
Oh, no.
So from 8 options, we're only going to take 3 at a time. You get 336. So I'll just go through that again. So first you press the 8 key, then you're going to go math, over to probability. Number 2 for NPR, and then after that you put in the number 3 and enter. You should get 336. So it's just another way of using the fundamental counting principle. Let's just talk about 0 factorial for a second, and then we're going to try and figure out a few more permutations. So if we replace r by n, in the previous formula, we get the number of permutations of n elements taken at n at a time. So we know this is n factorial. Okay, just like if we were looking at the word cat, there's 3 letters, we're taking 3 at a time, so it's 3 factorial. So if we have n permutations taken n at a time, that's n factorial. Expanding that, n factorial, if we're looking at the formula from the last page, it's n factorial over n minus r factorial, right? That r is now an n, so that's also an n. N minus n is 0. Are we allowed to divide by 0? No. 0 factorial will have to equal 1 if we started with n factorial, this has to equal n factorial. So 0 factorial just equals 1. Okay, so that was just a little proof. I'm pretty sure you can calculate that though. So if we go 0 factorial, it should work and show you 1. So if you forget, you can always just use your calculator. Alright, in a region, vehicle license plates consist of 2 different letters followed by 4 different digits. The letters I, O, Y, and Z are not used. Determine how many different license plates are possible. First, we're going to use the fundamental counting principle. So 2 different letters, and then we have 4 digits. For the letters, we can't use I, O, Y, or Z. So how many letters do we have? 22. Okay, and just keep in mind the language here. It says 2 different letters. So if I've used 1 letter, that means the next option, or the next letter will only be 21 options for that letter. So for the first place, we had 26 letters, but we can't use 4 of them, so we only have 22 options. If I've used 1 of those letters, I now only have 21 options. Okay, and then it says followed by 4 different digits. So the first possibility could be 0 to 9. So there's 10 possible digits we can choose. Keyword, different digits, which means you can't repeat them. So if I've used a digit, now I have 9 choices. Use 2 digits, now I have 8 choices. Use 3, now I have 7. So now we just multiply this through. Should get 2,328,480. Just verify that if you'd like. Now let's use permutations. So for the first 2 letters, or the first 2 places in this license plate, we have to use letters. There's only 22 letters that we're allowed to use, and we only have 2 taken at a time. Then we're going to multiply by how many digits are possible. Taken 4 at a time. And then we can just calculate. Let's leave that up there. Okay, so let's calculate 22 permutation 2. And then we're going to calculate 10 permutation 4. These numbers need to be multiplied. So we have 5,040 times 462. And again, we get 2,328,480. Okay? Okay, the last question of the day. Algebraically solve this equation where we have permutations. So we have to recall that n permutation r is equal to n factorial over n minus r factorial. So n minus 1 is like n factorial. That's going to go on the top. N minus 1 factorial. Divided by n minus r. Well, our n is n minus 1, and our r is 2. And all of that will equal 90. So we have n minus 1 factorial over n minus 1 minus 2 is n minus 3 factorial. How can I simplify that? Well, I can expand n minus 1 factorial, and I get n minus 1 times n minus 2 times n minus 3. Do I keep going? Why not? Because we have n minus 3 in the denominator. So let's stop there. Okay, n minus 3 factorials will cancel out. And now I have n minus 1 times n minus 2 equals 90. So to solve, we're going to have to expand. We'll get a quadratic equation. And then set it equal to 0 and solve. So I have n squared minus 2n minus another n is minus 3n plus 2. Subtract 90 equals 0. So n squared minus 3n minus 88 equals 0. So two numbers that multiply to 88 and add to 3 would be 11 and 3. Or sorry, 11 and 8. So let's use negative 11, positive 8. And n will equal 11 and negative 8. What do I have to remember? N has to be a natural number. Okay, so my solution is n equals 11. So when you are taking n elements, n at a time, you can use the fundamental counting principle.